be little experiments because we actually broadcasted this invitation to everyone in the world to join. And we're planning to post this on YouTube later on for people to follow up if they're interested in the content Farzaneh will present. So I'm going to start recording now. And if anything will occur during the meeting that you prefer we edit out, you can reach out and we'll do that. So it's just want to acknowledge that aspect. Is it already recording?
Oh, yeah, sorry, I'm just excited with your introductions.
Okay, so it's a really great pleasure to have Farzaneh Najafi visit us. So Farzaneh is familiar to many of you. She worked at the Institute for multiple years and I think left in 2023 to start her own lab at Georgia Tech. Previously, she was doing a PhD at the University of Pennsylvania on the cerebral circuit, and then moved to work with entrepreneurs on decision making and did some really interesting experiment reporting sensory and inhibitory neurons at the same time. And then she moved at the Allen Institute to help us do analysis on the behavior data that we released. So I'm sure there will be a lot of interesting presentation today that are related to this work. In addition, we are working with Farzaneh on our predictive processing community project, where she is contributing, potentially contributing to experiments and the experimental design. So welcome back.
Thank you. Thanks, Carol. Hi, everyone. It's really nice being back here on the 6th floor at the coffee. I was really excited. Okay, so this is the very first, the first major paper from my lab. I started my lab in 2023. And this for, the lab is all about, we're trying to understand predictive processing in cortex about our circuits. And we have different forms of behavior, motor behavior, perceptual behavior. The common theme is that there are elements of predictions and qualitative predictions, and we want to see how across the corticocerebellar loop we form these distinct forms of internal model, and we update it. The very first project for me was to understand some of the findings that we had at the visual behavior team, and they were very interesting but very puzzling. So this is on that. It's a passive behavior. And as you can see on the title, even though our lab is about predictive processing, we found evidence against temporal predictive processing in passive behavior. So I'm not saying as a general thing, but that's specific paradigm. The work is now in bioRxiv, and each one is my PhD student who took the lead on it. He got a lot of help from other lab members for running experiments and the engineering support, but he was really the primary person doing all the analysis. Okay, so a little bit of literature review and why we started this project. This first part here is the work at the Allen. So passive behavior, mice receive these like string of visual stimuli with occasional emissions. And then in a multiple work, it was shown that the ramp, and when I say they, I mean mostly VIP neurons, but also excitatory neurons in the visual cortex, but also higher visual areas like LM and all layers. They ramp before a familiar stimulus. Like this, they're inhibited by the stimulus, and if an occasional omission occurs, they just continue ramping. So this was the very, very interesting and puzzling finding for me, and the very most straightforward way to look at this data was that these are prediction error signals. Predictions, this is an anticipatory pre-stimulus like ramping that predicts the occurrence of the stimulus. And then this is either a prediction error signal or a continued prediction of the upcoming stimulus. So that's how I looked at it. But then, of course, it needed additional testing, and that's the part that we did in my lab.
First, can I quick question? You have the word passive up there.
Correct.
But you mean active? I think this is during the behavioral task, so it's.
It was both, because this data was found, actually this figure that I'm showing is the work that.
Marina's earlier work.
And I got the passive sessions for that.
Got it, okay.
But you're right, but the idea is that even that same ramp and omission was seen in the passive data set, yes.
There is a subtle difference.
That the mouse had seen them and they used, but
That they were used in an active sense before.
correct. But my understanding from talking, and Jerome can confirm, that in Saskia and Jerome's, like that paper, that was only passive and they still had that. So from my conversations with Saskia, so you didn't need to have that interval. Yeah, correct. Awesome. So how about other people? So this is your Keller and work, also recent work from Sonia Hoffer's lab. For them, it's a virtual corridor. The mouse runs through the corridor and then receives reward at the end. So it's not that they are making a decision about the stimuli that they are seeing, but there is a behavioral relevance potentially to the stimuli. And the reason I put all of this is that because at the end I want to come back to this and see that what is it that they saw that we didn't see. So the details of the task matters. If the virtual corridor stimuli, they watch it as they walk through the tunnel, and then occasionally they do an omission. The definition of the omission also is very important in the field because people use it in different ways. At the Allen, by omission, we mean removal of replacing of the stimulus with a gray screen, right? And we have that here as behind all of this. In Pure Keller and this new paper by Sonia Hoffer, the same thing. They remove it and they replace it by a gray screen. And then in these papers, they clearly talk about mission neurons. Also, they say that if one of these stimuli is unexpectedly removed, then you see neurons that respond. And then we go to this other recent work from Jeff Gavornik's lab, and this one I really want to, like, again, as I say, come back to this and see what is the difference. So in his lab also they're doing passive. Now for them it's not like the Allen that we had the individual visual stimuli, it's a sequence, ABCD. And then sometimes for them omission has a different meaning. They don't mean replacement by a gray screen, they mean extending. So omission is like this, do you see? So they extend, they make the stimulus longer. That's a very big and important difference. So this is one of the problems in the field, that people use omissions in different ways. And then they show that when they move from naive to trained animals, do you see this red? There's this continued response, which they interpret as a negative prediction error signal. So red here is when the omission or the extended stimulus happens in a naive mouse, they don't see a response. But when it happens in a trained mouse, they see extended response. So let's come back to this. But the main point here is that different pieces of work, whether a virtual corridor, whether a sequence of visual stimuli, or whether like the Allen, these individual visual stimuli have shown that there are ramps and omissions that have been interpreted broadly as prediction error signals. And that's how I used to also look at those. And now we might have wanted to see if that's really the case or if it is something else. So the idea is that when we have
I think it's unbelievable.
to remove the thing on this side,
I think that can be done. There is no way to remove it from there.
Way to.
To remove that, because it's a sign that.
I guess the top bar, we can remove it. I do see an X. So that one maybe.
See,
Okay.
oh, that one? Oh, well, but the room sign is not gonna.
But
Okay,
it's not covering the.
I love it.
Yes.
Because it's standard, yeah. But I understand, I also get bothered with the thing. Anyway, so what's the question here? We have a sequence of stimuli, and when I say sequence, I mean like repeating stimuli. At each time point, what is it that the neural activity is representing? Two things we can think of. One is that is the elapsed time since the previous stimulus, So how much time has passed, and that's what I'm going to refer to as temporal signaling. And the other is expected time until the next stimulus, basically how much time is remained until the next stimulus. So when we have these repeating stimuli, each time point could be a radial activity, could be one or both of those two. And the second one I call temporal predictive processing. Okay, is it clear so far? Because this distinction is important. One is about time passed since the previous stimulus, the other is about expectation of the timing of the upcoming stimulus. And in the temporal predictive processing, there are two additional things that come with it. That if there is a violation, like the stimulus was supposed to happen here, but it happens here, now we deal with temporal prediction errors that come in two forms. One is they call negative temporal prediction error, meaning that the stimulus was supposed to happen, but it did not happen. That's the unexpected stimulus omission. And the other is the positive prediction error, which is the stimulus timing is unexpected. It happens later. So at each time point, two types of signals could be represented: time elapsed, time expected, and the temporal predictive processing does come with these additional assumptions about the prediction error signals. And the idea was that we are seeing all these ramps and emission signals. What are they? Could it be one of these two? And we're just being confused. So the paradigm that we did in MATLAB is similar to the OWLET, but it has some important differences. One is that our mice are not on a disk. They are in the ideal tube, so they are sitting. That's one difference. The other is that we're using both auditory and visual stimuli. They are simultaneous. You may ask why. The main reason is that, as I said, the projects in the lab are very much corticocerebellar, and especially we focus on the cerebellar interactions with the parietal cortex, and parietal cortex is best suited for multimodal stimuli. So this is more for relevant to other projects in the lab, but that should not affect our results at all. The fact that the mouse is sitting, maybe that could be something, but let's keep that aside for now. And then we use 2-photon calcium imaging. We do it both from the visual cortex and from the PPC. Just a little note here, we have not done intrinsic imaging and the visual cortex that I say here. After we did histology, it actually turned out to be the area PM. So by visual cortex, I mean just broadly visual cortex, and specifically, if you wonder, it's the area of here, higher visual area. PPC was with A. So by PPC here, I mean with A. And we were interested in the activity of excitatory, VIP, and SST neurons. The way we did this was one, taking a mouse that is VIP TD tomato and injecting GCAM8F. So with this mouse, we get VIP and non-VIP, which we can say presumptive excitatory neurons. And then we had another mouse, SST cremite, that injected GCAM8F. So excitatory and VIP are simultaneously recorded in one mouse and SST in another mouse line. And then we did these in separate mice for visual cortex and for parietal cortex. The methodology is clear? Okay.
Yes, just that most of the time when you expect to look at these, you want to look at areas which are different in hierarchy. So this PM and this A are someone.
They're anterior posterior. So the main difference, so PM is posterior and then this A is anterior. So you can look at it as anterior and posterior of the whole these visual parietal areas.
Yes.
And there is a difference also in hierarchy, like with PM. So this A is further up than PM. But
they are very close to each other.
actually, they are very good
No.
in terms of function.
In terms of functional hierarchy rather than necessarily anatomical location. They are on different streams and they are not super different in terms of the depth. So they
Yes, sure. Okay. So, and these are some example responses: excitatory, VIP, and SS.
Application, so you did not report for V1.
Not V1, this is PM, correct? Yes, yes, sure. PM and yes, and then we just refer to that visual, right? Okay, so now the key part of our experiments are here, because if we really want to understand if these are predictive signals, we need to do very important experimental manipulations. And that's what we did here. One, we had these session types where we have blocks of troubles with short intervals and long interval, and then we transition between them. Each block is something like, I guess, 200 troubles. And why did we have this? The idea was that when we transition from one block to the other block, there is if we are looking at this from the perspective, from the lens of predictive coding, there's a prediction violation of the interval, and then new predictions should emerge within each block. So this paradigm was designed to see whether we see prediction errors at block transitions and updating of predictions within each block. Then we introduce another type of sessions, which we call them fixed and jittered sessions. And here, now there we were modifying basically the mean of the distribution of the intervals. Here we modified the variance of the distributions, but we keep the mean the same. So we had blocks of trials, which we call fixed, that all in stimulus intervals were 1.5 seconds. By the way, I didn't say these stimuli are gradings of 4 orientations, and each grading is 200 milliseconds. And what I'm showing here is the interval. So the way we study temporal predictive processing is by changing the interval between stimuli. So that's the key thing.
Quick question, Farzaneh. You said there's 4 orientations in a, is the orientation consistent or is the orientation kind of?
We have many blocks that we keep the orientation the same, and then we change it.
Okay.
All the analysis that I'm showing is focused on the intervals. So here we are not doing anything on the stimulus identity. And the reason is that that was the next step for me, that if we see temporal prediction errors now, let's see if there is anything stimulus specific in there, but we didn't see the initial one. But we're still analyzing that data, but that will be first. Right? I don't have that in this talk.
Okay, and the short versus long, you said short was 1.5
1 second
seconds.
and 2 seconds.
Ah,
So 1 second and then 2 seconds, and it stays there for about 100 or 200 troubles, and we can switch.
Sorry, just maybe I
Sure.
missed it, but what is the distribution of the jitter around the mean?
Sure. So the jitter here is a uniform distribution that goes from 500 to 2,500 milliseconds. The mean is 1.5. So this fixed block and this jitter block both have the same mean, but they are very different.
Each tribe is independent, right?
Yes, it's entirely random. There is another key point about these fixed jitter sessions that we introduce these deviant ISIs, or I used to call them alphas, but then because alphas are used with a very specific meaning in the field, so now we call them deviant ISI trials. So as you can see, those are the black ones. So the majority of the trials are 1.5 second, have 1.5 second interval. And when I say trial, I mean the stimulus followed by an interval. But then there is 5% with either long deviance at 2.5 or short deviance at 0.5. So as you can see, the deviance shown in black here are the edges of the distribution of the jitter blocks. So what this means is that these deviants in the jitter block are expected. They're not unexpected, at least, because they're already within the distribution that the mouse has seen. But in the fixed blocks, they're completely outliers. So what would the predictive coding idea say here? That the deviance in the fixed block should induce a strong prediction error signal, but not in the jitter block. Correct? There is another prediction that the stimuli in the fixed block should be completely predicted because there is entirely temporal regularity here. So the first session type, which we refer to as short long interval sessions, addresses the question of like these are both fixed intervals, but we change the mean and we want to see how the math adjusts the prediction from one block to the other. And then here we want to see how strong are the predictions, but also prediction errors between blocks which vary in their variance of the interval. And then we introduce another session type, which we call random interval sessions. The mice that we tested here were entirely naive. These mice had never seen any form of grading or temporal regularity. We put them in the session and we give them this distribution, which is exactly like the jitter of the fixed jitter sessions. It varies from 0.5 to 2.5 uniform distribution, everything random, orientations random, nothing is predictable. So the idea is what? That mice are naive, they have never seen any temporal regularity. Temporal predictions should simply not exist here. So with these three paradigms, we thought we're going to really see if these ramps that we see are temporal predictions and if the omission responses are at all related to temporal prediction errors. And what I can say, and we're going to go through the data and we will all see it, but it's about 2 years that we keep doing more and more and more and more, and we just get confirmation that these are not what we thought they are. Okay. A little bit on the methodology here, because the clustering method that we use is matters for the conclusions that we make. So we have the individual neural responses. We get the entire session responses. And whenever I say we here, it's really each of my PhD student with all the students in analysis. So what he did here, he applied the GLM. It was a simple GLM because all we have here is just this stimulus to see how to extract these GLM stimulus kernels. So he extracted the GLM stimulus kernels. And then an interesting thing that he did here was that he applied this temporal receptive field model that has been used in the literature by multiple labs. A lot of hippocampus labs use it. The model is simple. It's a convolution of an exponential with a Gaussian. And the idea is that we want to find ramp up and ramp down responses. That was one of the key things because I'm doing a little bit of not showing you the data, but showing why we use this cluster, because as we see, we have a lot of ramping in these neurons. So with this temporal receptive field model, he was able to extract ramp up from ramp down neurons. And then we get these two broad categories, and now we wanted to get the subcategories because not all ramp up neurons ramp up at the same speed. Same for the ramp down neurons. So now we apply k-means to each of these categories to get the subcategories. So the gist of it, through this clustering methodology, we get ramp up and ramp down neurons, and we are going to look at them, so stay there with me. And then we're going to get subclusters by doing k-means on top of this TRF and GL.
Can I just like, maybe go just like, maybe want to discuss this in the discussion, but why focus on ramps? Because like, if you focus on temporal expectation, the only thing I need to build a clock is just that the activity is not like self-intercepting, right? Isn't this just like biasing you towards looking at a very particular way of looking at time, like really just general population?
Because if I show you the responses, and that's what I said, that we didn't start with that. We did it after we looked at the results. So we've gone through a lot of different ways of clustering, but maybe let's see this and then ask me if it doesn't yet convince you. So let's look at the responses to the stimuli. In case you're wondering which one of those sessions I'm showing you, this is the long block, because that gives us a very clean response, a good 2 seconds, and we can look at everything. But at this point, the main thing I want to convey is how neurons respond. I'm also only showing mostly PPC, sometimes I switch with the PM, but they overall have pretty similar responses. So we have all those figures if you want to see, but I'm just showing one of the areas here. Okay, so what I show here is the average for each cluster. These are the individual clusters and the individual neurons. So 1, 2, 3, 4, 5. And then these are the ramp up. So stimulus comes, these neurons are inhibited, and then they ramp up. In the paper, we use 2 terms interchangeably. We call this stimulus inhibited or ramp up because they really go together. See, stimulus comes, inhibited, ramp up, inhibited, ramp up. This is another one with a different kinetic, like this one ramps up earlier, that one is later. And then these are the stimulus activated, or we say ramp down. So this is something that we just called in the lab. Because I just wanted to say that many times we call ramp, but these are really inhibited up or excited down. So this is a fast stimulus excited and a fast ramp down, slower ramp down, and this one is even slower. And if you want, these are the averages and these are the individual neurons. You can kind of see like the ramp up right before the stimulus. This has further, like a longer ramp up. This one is fast, transient. This is more prolonged. And this one is just little response and lasts longer.
And here you're showing us responses at in the middle of the sessions, giving, does it matter?
So we do that analysis for the random sessions. Here it's just everything,
Average.
everything is average, right? Across all these are all fixed intervals of 2 seconds across all of them.
Makes sense.
So the main goal I want you guys to get from here is how the neurons respond in general. Some are inhibited on ramp up and some are activated on ramp down, and this up and down happens at different rates. Back to your question of why we did that, because we really, and you'll see later and later it becomes more clear, we really wanted to focus on these, on the kinetics of these ramps. So that's why a temporal receptive field model that gives us parameters about the temporal weight, the temporal slope with a lot of things. But we have tried maybe 5 different ways of clustering, and that doesn't change the results. Okay, so now let's look at a little bit of how different types of neurons are there. Remember, I said we have 3 cell types. The clustering was done on all neurons pulled together, and then we looked at the distribution of the 3 cell types. So this is first, how many neurons go in each cluster. As you see, we have in general more in the stimulus activated clusters than stimulus inhibited. The numbers were different between Viz, and when I say Viz, I mean PN, now everyone knows, between Viz and PPC, Viz had more stimulus inhibited, but overall not big differences. And then this is the distribution. As you can see, and this is aligned with the Allen data, most of the stimulus inhibited, you see VIP, this is the stimulus inhibited cluster, a large contribution from the VIP neurons, very much aligned with the Allen data. Also from excitatory, much less from SST, and we had the exact same thing at the Allen. And if you look at the stimulus activated, SST loves the stimulus. That's what everyone also saw in the visual behavior thing here. But we see more stimulus activated perhaps than what we had at the Allen. We also have quite a good 30% VIP neurons that are stimulus activated and also excitatory. So, but overall, these findings are aligned with what we had at the Allen. Yes.
Technical question. So GCAMP has a slow decay time, so you're bound to see the decrease after the onset of the stimulus. So how do you take that into account?
So one, we use GCAMP 8, I guess it helps, but maybe not as much. 2, the way we took that into account was by using intervals that are, our minimum interval is 0.5 and we go all the way to 2.5. So we're trying to design the task parameters in a way that are suitable for GCAMP. So we're not doing anything fast here.
But you're bound to see a decreased ramp just due to GCAMP decay, right?
Decreased ramp, but we do see also an increased ramp.
I know, but how do you take that into account when you're not?
So are you saying that if these were EFIs recordings, you would not see ramps? So I think that's a very interesting question. How would this, because as you say, in our individual, this is not something we're getting from the average. Individual neurons do show this prolonged activity either before or after the stimulus. How would this look in EFIs data? I think they will look like sustained activity that gradually goes down. But I guess your point is that maybe not necessarily. Maybe this is something that GCAMP is giving us.
Well, you could fit with a GCAMP kernel like
To do inferred spikes?
Yeah, but
We did a little bit of that, that didn't change the results.
Good.
But I don't think we also have any good inferred spike algorithm out there.
Good.
But this is a valid concern, Jerome, and not until we do the thing, we will know the if it's.
You can kind of see that there's like fast fluctuations, like the last plot, you have fluctuations more than like 15 seconds, which kind of gives credit to the slower ramps probably.
You're in here,
Yeah, in your plot, next to 0, there's like a very fast
this,
deep, yeah,
yeah, and you say this gives what?
like it shows that you have resolution around those small
Right.
times.
Yeah.
So the other longer ramps are likely
Yeah, I mean, this is Terry Harris recording, so, yeah. So the types of responses that we see are these, and then now let's get to these three different sessions on this. So we talked about the short long, right? 1 second, 2 second logs, 200 trial, actually 50 trials, I guess these are. And then how are the responses? Number one, comparison between short and long. Now I'm not getting to the transition. So blue is the responses in short, green is the responses in long. And we can all see that whether in the ramp up neurons or the ramp down neurons, green is above blue. So overall, when we increase the interval, the responses become larger. And it's very clear also in the heat maps, you can see it. Why does this happen? One could be a boring interpretation that it's just a matter of resource availability. I don't think that's necessarily the case because we are already talking about long intervals here. Even for our short, like after 1 second, these vesicles must be replenished. So I don't think we are in that range of few or tens of milliseconds that we might be dealing with that. So the responses do look larger. It could be a way of encoding the interval, but it's a very robust result that we see. The longer the interval, the larger the ramp amplitude, whether it's ramp is seamless inhibited or seamless activated. This is a,
Yeah, these neurons clustered on one block, and then the same cluster was applied to the other block.
on everything in the session because the GL internal that my student defined, he used a long, window that covers both. So it's based on the stimulus driven responses. Yeah, it's based on that, everything. We didn't do the clustering across different session types, but all short, long sessions pulled together, turning around the stimulus cluster.
If there's differences in responses across the two blocks, that will be captured by that.
That's what we are going to show, but that should not. So you're saying that, and by the way, he also did the clustering first on short long. So yeah, like really a lot of detail here analysis. Those things didn't change. Yeah. Okay, so we have that. We know that overall the responses are larger after longer intervals, but the big question, how do they adapt between short and long? Because remember, the idea was that there should be a prediction error and a gradual emergence of regression.
Clarification. Are they only cluster of the excited neurons?
So we did the clustering on neuron, then 3 cell types pooled, and then we looked at what how much contribution we get from individual cell types.
Makes
We did not, but again, we did in the type of parasitatory and things. But the reason we're showing is that this is a cleanness. Yeah. Okay, so how do responses change from short to long? Let's look at these together. Let's look at the very first one. This is short to long transition. This neuron is the type that is inhibited. We actually don't see much of it around inhibited. The very first long interval here, right? What's happening here? Now we start seeing this ramp. And this is what me, Marina, and all of us at the Allen saw, and we thought this could be an omission-driven response. And if we see it, like this goes down, and there is that response here. But then could be a prediction error signal, we don't know, but then we continue looking at this and it doesn't change. And I forgot to put the bar from the end of the plot, but you can see the quantification here. So this ramp exists, but it doesn't really change throughout the block. So we looked at this and we are like, maybe this is a temporal prediction error, but it's a little bit surprising that in the next 15 trials, we don't see a change. So these are the last ones in the last 5 in the block. And this is the first 5 after the block. So it's like after a few trials, we have this drop and then it stays continuously throughout and things look like minimally different from the beginning to the end of the block. So you might say that, well, maybe this is a prediction error. But even if it's a prediction error, you would expect the magnitude of this ramp to go down. But it's for these alternative hypotheses that we ended up doing multiple manipulations because this was not convincing. It was surprising in the sense that the ramp didn't change at all, unlike what predictive coding scenario would bring. This other neuron was even more like a prediction error neuron, perhaps, because the ramp is more aligned with the mission, but this is because this is the one that ramps later. Let's look at some of the seamless activated ones. Seamless activated, this comes, nothing happened. Next one, there's a big response. I already showed it to you that when we extend the interval, the response magnitude goes up. And then again here, and you can see in the other one, there is not really much of a change in the amplitude of the response across the board, going against the idea of some learning emerging in the session, learning of the new interval. This other one with the more prolonged response, also we see that larger, it drops further. Now that we allow the interval to be extended, it drops further, and we don't see much of a change across the block. And for this other one as well. So the key thing we learned from this was that there is not much of a change that happens within a block. So it doesn't seem like that prediction errors are going down, predictions are increasing. But I was thinking that there could be a scenario that a neuron is encoding both of these. So prediction error goes down, prediction goes up, these two just cancel each other, and that way we don't see a change in the session. So it was not conclusive at this point to say that this is no temporal predictive coding, but it was weird. It didn't look also normal. Now let's look at long. Are the results here clear? So what we learned from long? Yes.
So your measure of change in a block is just defined by the amplitude. But you had mentioned there were other response kinetics that seem to be changing based on these plots that you're seeing. Like the first one, it's like they kind of plateau ramp and they start early, but then in the long sessions, they start later. Did you also?
Yes, we did that other measure, and thanks for saying that, because we did that analysis, but then in the soft level figure, and now I think we should add it. So we did that response similarity and also correlations, and it confirms this.
Okay.
But it was the simplest measure, so, but I really think now I should go back and put it in the soft. But yes, we have them.
Okay, cool.
Okay, so long to short transitions. Now we see these very clear ramps. And then the stimulus is introduced early, and this was initially very surprising to us, because now the ramps look much smaller. It even seemed like now we are moving to a regime where the neurons don't ramp as much. But again, there is clearly not a positive prediction error response. There is nothing that like a big response here, and the responses don't change within the block either. Same with the other type of ramps, neurons. So some of these seem like these were very intriguing, like the second cluster to me, because this cluster just runs in the long block, not in the short block. No sign of prediction error, but there seems to be a change of just response profile between the long and short. But all of this eventually made sense to us what's going on here. With the stimulus activated, there is not an increase in response, but the response just goes down, which is aligned with the idea of larger responses after longer intervals, and not much of a change really within the block. Same with this other one. With this, like this one seems not to be much stimulus driven even in the short block. So the block transitions were not conclusive in terms of whether we have temporal predictive coding or not. They were conclusive in the sense that we didn't see a very clear signature of a positive prediction error. We definitely didn't see a signature of a clear adaptation within the block. And by adaptation, I don't mean stimulus specific adaptation, I mean learning for new predictions emerging. Anything was very rapid on that, whatever happened on that very first presentation of the error continued throughout the block. So it was a very immediate response change in both block type transitions without any sign of learning. So that's what we learned. And then,
So I think to me, it looks like there's some transition effect, especially when you move from long to short.
Right.
It's like a fourth cluster or like first cluster, and even have some.
You mean
changes
this,
for
that it goes a little bit higher?
Yeah, why would you say there's no learning effect there?
Because of everything else that came after that. Okay, so learning, I agree with you. I mean, it would be not quite correct for me to say that this is not different from this. It does seem to be going up a bit. with the correlation and stimulus, like response similarity analysis that we did, they didn't show really a difference here. So you could see this rapid adaptation. I also am not exactly clear how to read into this enhanced response here. It's not relevant to our temporal predictive processing, but yes, maybe there is some change. Maybe for some of them, not for all of the clusters. Some really don't show, like this doesn't show it at all, right? But some of these do show it. So yeah, maybe I should tone down when I say that there is no change. There is nothing happened here that would be aligned with learning the new interval.
So I think that there are some changes maybe in some
In some
cases,
of
but
them.
it's not consistent with your expectation for prediction,
Exactly.
temporal prediction.
And also overall, so see like in how many of these you see, I don't see it here, I don't see it here, not here, not here. This one like something very, so it's really, we're talking about one in all of these that is showing that. And even this one, it drops down, so we can also show them. And as I said, the other measures didn't show it clearly. So I also don't know how much I believe in this as a real response. Yeah. So far the block transitions did not show signs of, especially positive prediction errors. With negative prediction errors, we might say there is something here, and that's why we went to the fixed jitter plots. So I think the fixed jitter plots are the nail in the coffin here, and you see why I'm saying this. So the prediction. The deviance here should be way more strongly encoded than the deviance here. And the predictions here should be substantially stronger. Here I don't even expect to see a prediction. Now let's see what we saw. So this is in blue, I'm showing the jitter, and in red, I'm showing the results from the fix. This is aligned on the stimulus before and after the long deviance. So both fixed and jitter have this. That's why we can easily align them. And what you can see is that in both of them, we see this decrease. And this is the key result, that they are extremely similar in how they rank. So in the jitter, remember the omission in the jitter was just one of the many intervals that they had seen, but there is no difference. So this is why I call this experiment the nail in the coffin, that these are not temporal prediction errors. And not just that, also the ramp prior to this stimulus is very similar. The one before, you see the difference, that's because of the jitter by definition. This one was jitter. But this one, so what they are doing is that it's like a very stimulus-driven dynamics. It's inhibited and ramped, and they don't care. They have not learned anything about the statistics of the intervals. They do the exact same thing, whether it's fixed or jitter. These other cluster, the stimulus activated ones as well, like similar. These are just, we know that we're not making any mistake because of this, because here they separate, and that makes sense because the stimulus did not exist for jitter here, but you can see that there is no difference in how they ramp prior to the stimulus or to the omission. Yeah.
Two questions. Can you unpack this plot on the left? I'm not sure how you're plotting the jittered, if they're like a bunch of, random ISIs.
Easier if I just draw it,
Okay.
and that won't help in the remote control, so I'm sorry about that. But the jitter is like stimulus, anything, right?
Yeah.
And then fixed is fixed. So now we have these long deviance. Right, and if I wanted to do this better, I would show one just like that, because remember the long deviant is just one of those.
Yeah.
And then here, just to make it. Let's say these are fixed. And then we have the long deviance, right? And then the one after here is just similar that. I mean fixed, right?
Yeah.
And the one after here could be anything.
Yeah.
So these will be aligned, these two, right? And that's what you see, those two gray bonds.
Okay.
And the one before will not be, And that's what you see.
Oh, I see.
And
So
people-
you don't see the responses in the
Exactly,
blue.
because it's
Okay,
averaged out.
Yeah.
But I put an empty box there, so we can see that that's the average of when the jitter happened, and that's when the fix
Okay.
actually happened.
yeah, that makes sense.
And then we're looking, and this is the expected based on the mean for jitter and the individual.
Okay.
So that's yellow is the expected stimulus time.
And then I guess my second question is, did you do a version of this experiment where you started with the jittered?
So some sessions are different, some fixed jitter, some jitter fixed.
Oh, okay. Okay,
Yeah.
got you.
And the sequence of the sessions that each mouse saw are not the same as what I'm presenting. I'm presenting it in the sequence that is so can be told better.
Mm.
We first started with the random because we wanted naive voice, then we went to fixed jitter, then we went to short long.
I see.
The key one is the random that has to be on naive. I'm sure at the end.
And there were no differences between the mice that had different block orders for the jittered and the fixed.
Would you, correct?
Okay.
Yes, it did not explain that.
Okay.
Yeah. So we were like, maybe this is average. Average is just one dimension as the data, and that's not showing it. So we did decoding, and decoding did not show anything either. So there's no difference between fixed and jitter relative to the shuffle. So here we are just decoding the block times at every individual time point. We train the decoder and know where we saw here. Then like, let's look at the PCA trajectories. So what my student did here, this is just the average, and the PCA comes later, but let's go through this together slowly. So he looked at the PCA trajectories between at this omission time, basically. So this is for the fixed. This is average of all trials and neurons. And this is for the jitter. We can see that these two look extremely similar, and these are the PC trajectories. PC trajectories were done on trial average responses. So we don't have temporal dynamics here, but let's go through this together for the fix. That's the start. So these go together. The idea was to make this easier to be understood by looking at that. This is the start. That gray is when the stimulus comes. There is a beautiful, you can see like, do you see the line is less jittery because it's the quenching of variability with the stimulus presentation that has been shown in the literature. So very beautifully it pushes the population into a state of lower variability. Then you see that's when the response starts relaxing back to the baseline, and we can see that. But all of these are on this side. This is when the unexpected omission happens. And you can see that this just continues the trajectory, it's not like anything special happens. And this is that late unexpected stimulus that just like that, it pushes the stimulus into this evoked state, and then it gradually goes back. Now let's look at the jitter. We start here, the stimulus happens, and then it pushes it to the evoked state. Then we go here, it relaxes back, the omission comes. Nothing happened, it just continues the trajectory. The second stimulus comes and it does that. And the key thing is between this yellow and red. That's what you see here, yellow and red, that's after the omission. And you can see that with both of them, what we see is that just continuing the trajectory. It's not that in the fix, when the yellow happens, this trajectory goes somewhere else. No, it just continues. And you'll see more confirmation of this when I show you guys more of these PC trajectories. So at this point, what we have learned is that responses to long deviance are independent of temporal predictability, because this is very much temporally predictable, this block is not, but the responses are just identical. And not just the long deviance, but also the ramps prior to the stimulus.
I'm confused.
Yes.
In the PCA analysis, did you run, is it a single run of PCA across both blocks?
No.
Is
So
it
what
two different vector decomposition?
to different,
Oh, I
so
see. Good.
it's trial. So do you see this?
Well, if it was the same, you would expect the trajectory to start the same. But I see the plots are,
Yeah, it's two runs of this.
so maybe you want to do a single run to compare more closely.
A single
Just
run.
a single vector decomposition across the entire session. plot the trajectory.
But then how do we compare?
You just plot the trajectory from the start, both cases.
Yeah, but then how do we compare excited? Because here, the way my student did this is that, so let's say we have two, sorry. So let's say we have 200 of these cases, right? And 200 triangles here, and let's say 100 neurons, and then we have like 1,000 time points. So he averaged across triangles, that gives him 100 neurons and 1,000 time points, and that's the trajectory that we see. And then he did that same thing here, and then we're comparing.
Same session, right?
Same session.
Right, so you could do a single PCA.
But then if you do a single PCA, then you will get a single trajectory.
No, you can project each
So
project.
right, to get the PC and the projected
That's right.
trial type.
That's right. I think that would be
I
it.
should ask him if he has done it, but yes.
From your plot, it looks like it's two separate.
Definitely two separate.
That's right.
Yes, for sure, he did two separate PCs here. Sometimes I will say it. It's possible that he has done it. Okay, so we are all, I guess, on the same page here that this showed no temporal prediction or prediction error because they are identical. And then how about the short deviance? Now let's look at this. So this is when the stimulus before the short deviance, and this is the stimulus that happened here, right? And then we were like, this short deviance should be more of a surprise signal in the blue, which is in the red, which is the fix. But the response after this short deviance is not different between blue and red. Well, in the stimulus inhibited, you can see it, and especially in stimulus activated, like look at this. So it's nothing like that. The red is, for example, only one because it was more unpredictable.
My question, can mice tell the difference because the variation is between like 500 milliseconds to, from the expectation at least, it's plus or minus 500 milliseconds, right? Is that right? From the expectation, the deviation in the.
So this is the distribution. It's black. Is
It's
the
like
one
1
that's
second.
it's 500 milliseconds.
So
And
like
then the
1
deviation is
second.
from 1 second.
The error is like of 1 second.
Yes,
Is
correct.
that long enough for them to realize that there is?
It's big. It's big. It's really big. I'm sure we're not talking about milliseconds here. We actually did choose something long for that exact same reason. But the way we did it was that we should be able to tell it. So we first tested it on ourselves. With 200 milliseconds, I guess I did it before, but 500 milliseconds is visible. Yeah, but that's it. And so I hope you can see that on average, we don't, again, for the short deviant also, we don't see a difference between the blocks that have high temporal predictability versus those with very low temporal predictability. Again, the decoding analysis did not show any difference. We could not think of fixed and jitter from each other. And then the PC trajectories, well, this is the average responses. And now let's go through the PC trajectory here. We start, the stimulus comes, it pushes in, the stimulus will gradually relaxes back, the new stimulus comes, and if you see anything like this, really doesn't look too different from that, except for the amplitude, which is well known that the amplitude increases. And then the key is to compare that with this. We start here, it pushes it relaxes back, and then it pushes it and it relaxes back, and the part after this red and that red, what we see is just on a stimulus activity. So responses to short deviance are also independent of temporal predictability. So at this point, it's like we don't see temporal predictions or temporal prediction errors. Now things make more sense for our short long transitions because these also didn't show. Especially here, there was no clear sign. There was no clear sign of a change within a block. And then we are like, maybe these mice have seen lots of these sessions. So even the jitter mice have seen a lot of sessions with temporal regularity. And so maybe what the mouse has learned is the mean of the distribution, that on the mean is the same, right? And so that's why they ran similar thing. Let me show that here. So the reason this ramp is similar is that the average of the interval is the same between the two blocks. So the mouse has, the internal model of the mouse is to predict the average interval. And so that's why we don't see a difference. But in that case, then the variability should be different. We looked at the variability, that's a supplemental figure, and we did not see any difference. So it was not like that on average, these ramps and omission responses are similar, but trial to trial variability, there was not such a thing. But we said that let's go and do this more carefully. And that's where we did the naive mice experiment. So we took these naive mice that never have seen anything. So these guys don't have an internal model whatsoever. And then what we see, to our surprise, again, we find these ramps, pre-stimulus ramps, like ramp up and also the ramp down, and some of them are fast, some of them are faster, some are slower. When we look at the distribution, I should say something that the overall number of stimulus inhibited or ramp neurons were less in mice that were never exposed, but they existed, and I will show more careful analysis after that. But if you remember, like here, we have like something like 60, 70% and 30%. But in the other case, they were still more stimulus activated, but more so of the stimulus inhibited neurons. Now, we see it in all the cell types, and like the change between the three cell types is less, even though still SSC likes the stimulus activated, is more in the stimulus activated cluster. Then we were like, these are the averages of, we have 5 random sessions that maybe they learn it again at some point, that there's this repeated stimuli that on average has an interval. So we compare the responses across sessions, the clusters. So you can see that the fraction of neurons in a given cluster, it's not like that we get more or less across these random sessions. And then we were like, maybe this is a very fast adaptation. On that very first session, they learn it. So before I go there, so let's look at this. So these are the across days, and you can see that they're super similar. So it's not that things change across days. In the stimulus activated, the yellow is not very well shown, but definitely it's a bit larger. So that is true that there is some level of stimulus adaptation going on here in that very first day of exposure to this stimuli. They had larger responses, but their ramps were similar, and the overall response was also similar. I have a question. Sorry. Okay, and then in day one, then we divided these. So my student looked at the first 100 stimuli and the last 100 stimuli. We love to look at it with more precision, and like, let's say the first 5, but it's super noisy and we couldn't do it. And I hope I can show it to you guys that even in the very first 100 stimuli, you can see that the ramps still exist. So it's really one after the other showing that it's not that there is a temporal prediction emerging in these responses. In the naive mice, the very first 100 stimuli, they existed. In between fixed time jitter, they were not different. When we transitioned, we did not see any sign of adaptation. And then we are like, then what is this about? What are these ramps about? If they're not about temporal predictive processing, what are they? And that was the thing that we went on the first day. So here we divided in these random intervals into 4. The ones that happen like very short, medium, long, something like that. And let's see what's going on here. We are looking at random sessions. Yeah.
Close to the hour, and just want to make sure.
Sure. This is the end of it.
Oh, okay.
Yeah. I will be fine. But this part, what you can see, I love these figures because it shows that here is the ramp, and let's see what's happening. The stimulus comes, it interrupts it. If the stimulus doesn't come, it keeps ramping. So you can very clearly see this idea of stimulus evoked relaxation. In some, the stimulus evoked is in the form of inhibition and ramp up, and in some other, it's in the form of excitation and ramp down. So let's look at this one. Excited, new stimulus comes, it goes up. If you don't allow it, it keeps going down until the next one. So what we see here is that in these naive mice, we see these ramp up and ramp down activity. And what's happening is that the stimulus here the stimulus interrupts, it resets the dynamics. So stimulus comes, sends them to an evolved state, they gradually relax back in the form of ramping down or ramping up. So it seems to be very much about like the time interval between these neurons. And these are the beautiful PCA trajectories that you can see. The stimulus sends them, and this trajectory continues unless you give a stimulus and you interrupt it. Do you see? So it's interrupted here. If you give a stimulus, it just continues. Stimulus pushes it out, but then it continues. So you can see that what we thought were these temporal prediction related ramping signals are simply stimulus-driven dynamics, which could be in the form of ramp up relaxation or ramp down. And then we tested this idea if these are really about the timing. So we trained a pairwise decoder for individual clusters to decode one time point versus the other. And this is the summary of those. So we averaged these. So this is easier given that we don't have much time. So what you see is that we can decode time from time that is elapsed from the previous stimulus. Each color is one cluster. But you see that the temporal profiles are different. So this cyan cluster, for example, does a very good job throughout the entire interval. On the other hand, these red-orange clusters, they only do a good job initially, and then they do a good job later in the interval. And we wanted to know what defines this, and that's where our temporal receptive field model came into play. That we can see a very nice progression of these temporal fields, whether they're ramping speed or they're ramping weight, that aligns with the temporal decoding. So I rushed through these last parts, but the gist that I'm trying to say here is that I hope that everyone saw and agrees that there is no temporal predictive processing, that everything seems to be just stimulus-driven dynamics. These trajectories happen, the stimulus pushes it out. If you don't give a stimulus, it just continues. So what we thought is that omission-driven response was only because we had extended the interval, so we allowed to see this profile better. And then we can decode time. I'm not saying that this is what the mouse does, but what I'm saying is that this information exists. So if there is a downstream region that runs a linear decoder on these activities, the timing information is available. It's a passive paradigm, so I don't know if this information is actually used by the mouse. There's no way for us to have a behavioral readout. But then a big question remains, and that is, do we have even temporal predictions in the brain? My guess is that we do, because as humans, we can see that even when we are not paying attention to a task, when there's like some beep happening in the background, if there is a violation, we notice it, even though we are not instructed to pay attention. So I think these temporal predictions and temporal prediction errors must exist somewhere in the brain. We are testing the cerebellum for that now, because cerebellum is a big timing area in the brain. And second, we are testing this in the brain. So maybe in the active paradigm, because there is a chance that maybe not for the mouse, maybe as humans, we are tuned to this regularity and detecting any temporal irregularity. Maybe mice, their passive paradigm don't care. So we are testing both of these. And this is just a summary that there are these broad activated, inhibited categories and subtypes. There's an immediate shift across clocks. There's the temporal prediction and violators are identical, independent from temporal regularity. The ramps are in naive mice, even in random intervals. And then we can decode timing information from these clusters, and the timing, the decoder profile is tied to the ramp kinetics. What did we learn? During passive, visual and parietal neurons do temporal predictive processing. These dynamics are intrinsic, and they're about stimulus, reset, relaxation. Stimulus, reset, relaxation with diverse time scales, whether ramp up, ramp down, but it's all stimulus driven. What do they learn? We can rate out time. If that's what the mouse uses or not, we don't know. Putting it all together, this study sheds light on the true nature of ramps during repeated stimuli and unexpected conditions. demonstrates the necessity of careful experimental manipulations before we make any conclusive interpretations about predictive coding. So this is also another big message that we have in this paper, that many signals could really look like ramps, anticipation, or prediction error. But if we want to know whether they're really like that, we need these manipulations, change the mean, change the variance, look into untrained mice and see if things change. And the testable speculations that we have is that other regions, hippocampus, by the way, could be another region. They may have passive temporal predictive processing and active engagement may really show this even in visual and parietal areas. That is my lab. So the people who did it, and I also want to really thank some allied people that have been repeatedly getting in touch with them to get help on, like starting, and know there was lots of questions. Thanks a lot.
If some of you have to go in, it's fine, we can continue. Any questions?
Yeah.
Use the statistics of natural scenes 4 months ago.
So these are grading.
Yes.
Yeah.
But the reason is that what you provide is a set of curves. So the moment you're saying there's no adaptation, right? There is nothing which seems to be learned in order to do predictive coding. But it might be an evolutionary pressure in order to be able to do that, not on a learning basis, but on the statistics of the environment. Right, so you could theoretically create a repository of history of some elements of the information. So let's say that at the moment, I want to go into the visual cortex and understand what the mouse has seen now, 10 milliseconds ago, 100 milliseconds ago, a second ago, to some level of resolution. But what you're saying, the ramps which are putting it there, which seem to be irrespective of anything which is happening, seem to point towards trying to have an implicit history of the stimulus. That history of the stimulus, the way you'd want to code it in an optimal fashion, will be dependent on the statistics of the environment. One could reformulate predictive coding rather than as a learned system, as a default system. Sorry to try to move.
So what we're showing is that these are only stimulus-driven responses. You may say, why is it that for some neurons it's inhibited ramp up, for some excited ramp down? And I would say it's the AI motifs, the different microcircuits there. So, but you're saying there is some learning here?
No, what I'm saying, I think that you kind of proved quite clearly that there is none. Or there is very little, or whatever learning, whatever changes are going to be present is not consistent with predictive coding.
It's not consistent with alignment. Sorry, I have forgotten the yeah. So along with what he said, the RAM of neurons do increase across sessions. We didn't make a point about that because that was not aligned with. So there are other changes that are happening, but not related to predictive coding.
Yes, but theoretically, one could make as a way to try to think. I'm not necessarily trying to resuscitate the dead predictive coding right now, but just to say that there is a reformulation which can be present where you're going to try to create a way to try to think about coding, for example, of the history of the stimulus within the cortex, which I think you're showing. The type of responses which you're showing would theoretically have the capacity of decoding not only the present, but also some elements of the history, right? That is what you're showing.
Okay, when you say history, we actually looked at if two intervals before we didn't have that. It's just the one before. Stimulus happens, and we don't have two intervals back. We cannot decode them.
Right, at some point you're going to lose, right? You're not going to have within within your visual cortex.
But I mean, there's a trace, when the stimulus happens, there's a trace, so there is a memory, yes.
Yes. And the question which is going to be, are these types of memories optimized based on the statistics of the natural scenes for the mouse in order to have those types of things which are naturally present?
But if it is based on the statistics, why were they not different? I mean, we didn't quite do that comparison, but between, well, no, we did like fixed and jitter, the response profiles the various.
No, but again, not learned, evolved. Well, everything we have code is consistent with not learning.
We're not learning, yeah.
Yes, so from that perspective, you'd want to evolve a particular set of kernels in order to be able to represent things from the history, not learn them.
Right.
Or something that could be learned in the, like a very longer time.
Yes,
stage, right?
during development, other things like this, right, or things like this, which are going to be present, things which are no longer going to be modified right now, but things which are, set in stone at the moment.
It's how to test, no? But
Sorry?
this is how to test.
That's exactly why I asked if somebody knows if there is a data, right, for humans or monkeys. We've got plenty of databases. One can go on and try to understand all the distributions of orientations, receptive fields, and things like this, and you could easily, right? I think also some fields, for example, went on and created some implicit relations on theoretical models based on understanding the distribution of natural scenes. What I would imagine is that the type of data which you're having could potentially take pulsars and fields-like approach in order to try to understand is going to be the type of optimal code, but not for representing the now, but also representing the past. And that's why I started with the question to be able to actually test it.
I have a related question that is kind of similar, I think, because what you're saying is that there's maybe some characteristic time scale and whether this is not just time scale, but the ramps were kind of, just going up. My question is, what did you extend the time from 2.5 seconds to 10 or 30 seconds? I mean, it cannot continue.
Well, we did that.
Oh, yeah.
So it should not continue, but we tested it, I guess up to 5-7 seconds and stopped. And I mean, they start to saturate, but they really continue around.
That's pretty cool. So probably it's restriction time scales, and that's probably aligned with some kind of statistics.
So can someone help me understand Stefan's point to sentences? Like maybe someone.
That's what maybe.
So he's saying, okay, thank you. So you're saying that maybe the brain, given the natural statistics, the brain has learned this type of response.
Yes.
But then I'm proving that we also have different clusters, not all of them are the same. Like one of the key findings is that there are different ramp kinetics there.
But those would need, right? You're not going to have only one type of stimulus in the environment.
Yeah.
You're going to have a
Yes.
diversity with
Yes. Right. Sure. So you're saying that you think they're, I think it's very likely, I mean, the type of responses, and then a good testing for that would be whether there is a difference across species, because what
Yeah,
I see is
but
not.
at the same time, you probably want, it's not a cheap or easy thing to do unless somebody has already built a database of this kind of things. Right, so did somebody work, are there ethologists who looked to take cameras to put them in most environments to understand spatiotemporal properties or things like this, which are going to be present, right? Because you're not necessarily, if you think from humans or monkeys, I don't think that you're going to get a light temporal precision or spatial.
A few things we could do on those is maybe dark rearing animal or environment enrichment. And that's not going to still rule out the evolutional perspective, but I think we could rule out some of the developmental perspective on that.
You rate in the slow environment versus fast environment?
Yeah, and see the differences from a default cage animals.
I think it's very cool. But anyway, sorry.
Yes.
I was just trying to provide a theoretical underpinning for the things you see, right? Because it's not predictive coding. What is it? Why would you see these types of responses?
Do you find any and then temporal coding combination?
Yes. But it's again, I think that in the end, it would be the way I would find it the most convincing. You're probably familiar with the pretty famous paper from All Southern Fields, right? Relating
What field?
All Southern and Fields, I think was Nature 96 or something like that, 30 years ago. Now, in which I think was one of the most beautiful things in which they related some elements in terms of synchronization seems to the type of receptive fields which are present in a perspective of a code. And I think that potentially you could do the same type of thing if you had that statistics.
I have a follow-up question. With Andre Bastos and Max Meyer, we saw when we present different types of oval that oval equals, right? And so when we see that we have higher order statistics, they're not present in the visual cortex, but more like in higher order areas. And so I think it's been other types of stimuli, unexpected stimuli that have been shown to evoke really strong responses. For instance, like when you change the gradient orientations or the size of things. So I wonder, one interpretation is that the visual cortex is just not influenced from that temporal prediction.
Yeah.
That you will see the piece somewhere else.
Yeah.
Have you looked at, well, so that's one interpretation.
Yeah.
Right? And so when I wonder, if you look in your minds, did they actually detect, perceive what's unexpected events, like in terms of behavior
So
responses?
we have the pupil
Huh?
and we're looking at that. So not until we have the nice clean figures, I want to say this.
Okay.
Yeah, but we have that.
Because that would give both by looking into the cerebral and the hippocampus, you would see this.
Yeah, but even, okay, so let's say we finish our analysis and we see that there is a difference between face and jitter and the omission. Then yes, somewhere that perhaps should be an agreement.
Because I think that's a major discrepancy I see in literature is that everybody's designing a different experiment, slightly different experiment, and they want to test the same kind of principle algorithm across groups.
Yeah.
But in fact, all the program areas are equipped with the same information. So it's actually quite challenging to reconcile.
That actually brings us here, and I'm glad you said it because I've been very much. So this, I guess we have an answer about that because the paradigm we did in my lab is very much, we made it as close as possible to the Allen. And I think that explains what these were.
Okay.
But talking about other people's data is harder. I had a conversation with Georg and what he says, and I said that we don't see it, we actually show that there are no real vision responses. And what
His stimulus is very different.
no, there simply are also gradients.
No,
But in the context of a
they're
very close
changing,
correlative.
they're changing the grade.
But the omission, but they have also the omission. So that's why I put this, I actually went through the details of these papers very carefully, so
But
they
they're
have,
not just controlling, it's very different experiment.
correct, and then, correct, and then what he said was that for him, these are not temporal signals, these are spatial emission signals.
Visual.
Yes,
Yeah.
that is, which makes sense. So in his opinion, his data are not
It's a different,
exactly.
Prediction.
The key one is Jeff's, and I
Yeah.
would love to have a conversation with him. There is a big difference. Omission for him is extension. So that is one thing. The
Yeah.
other, but he does conclude that these are negative prediction errors. So in his paper, they very clearly say that we have negative prediction errors in a passive paradigm, which is opposite of what we said.
Again, this experiment is different. It's A, B, C, D. They're presenting sequences of orientation and then changing the interval between.
Yes, but even that, if you, so I agree that there, part of it is that, we are really testing.
They're not predicting time, but predicting the orientation.
But even there, okay, let's look at that now here. There is one thing in these figures that I wish were done, which is to put a line here, so we know where when the stimulus happens, but my guess is that they have the finding that we also have at the Allen that when there is naive, it's seamlessly moved. So I think the stimulus lines will be there. And then this is A, and that's sorry, I guess this is X, and then this continues, so then this seems to, because they don't have the lines, it's hard for me to know, but it seems like when, in a naive mouse, when the stimulus comes, even when it is extended, they just include the onset of it. That's what I understand. Then when we go to train, again, they don't have the stimulus lines. It's hard to know, but I do see a phase shift here. So it seems like they're seeing that phase become more on the pre-stimulus front, which is aligned with the Allen data. And then the key thing is that this continues, and they rate this as a continued prediction.
So you're talking about their omission, we represent gray screen.
But this omission is the continued. It's
The continuing of the,
Yes.
yes.
So the key thing, again, they are not showing us stimulus lines. That makes it very hard to understand. That's why I really want to just make Jeff and talk about this. But my guess is that the stimulus line will be somewhere here. So in their train, there is a ramp prior to the stimulus, which can easily be confused as a prediction, but I wouldn't say that until more experiments are done. But there's something clear that this, when they continue the stimulus as opposed to just ending it, this ramp continues. And my guess is that this can be explained by our findings, which everything is explained by stimulus about dynamics. So I think these neurons ramp prior to the stimulus happens, happens and then ends, and it's inhibited. In this case, it doesn't end, so it just continues. So I think this is not, I mean, this is a big claim. I don't want to get, but I think this can also be described with the stimulus about dynamics instead of predictive coding.
I would, I've actually got texted an email with Jeff this week, so just sign it as video.
Exactly.
And then ask him the
Yes,
question.
so I should have, I'm just gonna write him and say I want to know more about this and see if.
They do see this gigantic response when you increase the interval
Right,
in their favor, like this same result as you. Like when-
is this paper?
No,
This is the very recent one, this is on my work.
yeah, but he has shown to me that when you increase the distance in time between the oval, then the response goes insane, big.
But, and that's the one we.
So it could be surrounding, as you said, but
Right.
it just continues to, they have not pushed. I asked him, try to make it super long, how far can you go?
Right, yeah.
Nobody had nobody knows.
And one other thing that was interesting to me was that these experiments were really simple experiments. And it was interesting to me that we keep talking about these, I mean, but some of the simple experiments, like I couldn't find the papers that have done those. And so it seems like some of these very simple experimental manipulations are missing. And we're overinterpreting
It's
this.
not fun, yeah. It's 11:20, I have to make sure of it.
Thanks, everyone.
Thank you much. Thank you. So, we go back to lunch at 12, right? So anybody feel free to join the 6th floor if you want.